Hello everyone, welcome back to my VLSI diary. My name is Shivangi Upadhyay. In today's video, we will explore the VLSI design flow, the step-by-step process followed in designing an integrated circuit from idea to fabrication. If you are interested in chip design, RTL coding, verification, or physical design, this video will give you a clear overview of how everything connects together. So let's begin our journey into the fascinating world of VLSI design flow. Now let's talk about what exactly VLSI design flow is. VLSI design flow is basically the transformation of hardware description into a physical chip layout. It represents the complete life cycle of a chip, starting from an idea or concept and ending as a silicon that's ready for manufacturing. It converts high-level logic into a manufacturing physical design, ensures that the chip meets all PPA specifications, that means performance, power, and area requirements. This process involves both front-end design, which focuses on the logic and coding, and back-end design, which deals with the physical implementation. Overall, the design process follows a systematic sequence, which is RTL to synthesis, then layout, then verification, and GDS. So basically, VLSI design flow is the journey that takes a digital concept and turns it into the real working integrated circuit. Now, let's look at the flowchart for VLSI design flow. It all starts with an idea or a concept which define what kind of chip we want to design. For example, processor, a sensor interface, or a communication block, etc. Once the idea is ready, we move to the specification stage. Here, all the functional and performance requirements are defined, like speed, power, and area targets. Next comes design with architecture, where we decide how the system will be structured internally, such as defining the blocks, data paths, and control units. Then, in RTL coding, we describe the circuit behavior using hardware description languages like Verilog or VSDL. After the RTL is complete, we perform functional verification to ensure the design works correctly before moving to the physical level. Then, logic synthesis, where the RTL code is converted into gate level netlist, a circuit made of logic gates. Once this is done, we move to the physical design, where the circuit layout is generated, including placements, routing, and optimization. Next step is layout verification, which checks the design rule violation and electrical errors. After that, fabrication takes place, where the verified layout is sent to the manufacturing to create the silicon chip. And finally, we perform testing and verification of VLSI design to ensure chip meets all the functional and performance goals in real hardware. So, this flowchart represents the complete journey from idea to silicon, covering both front-end and back-end design processes. The VLSI design flow begins with the idea or concept phase, which forms the foundation of the entire chip design process. At this stage, designers conceptualize the product, identifying what the chip should do, its target performance, and design constraints such as area, power, cost. They conduct a feasibility study to evaluate whether the desired functionality and specifications can realistically be achieved within the available technology and process nodes. This stage also involves identifying design trade-offs. For example, balancing speed versus power consumption or area versus performance to ensure optimal design decisions early on. Once the overall system level idea is clear, designers define a high level system architecture, breaking the chip into functional blocks and specifying their interactions. Output of this phase is a specification document, a crucial file that clearly outlines all the design goals, performance target, and functional requirements. In short, this stage transforms a raw idea into a well-defined, technically feasible blueprint that guides the entire design journey from concept to silicon. Once the concept and feasibility are finalized, the next important step in the VLSI design flow is defining the specifications. This stage clearly outlines both functional and non-functional requirements of the chip. It specifies what the chip should do and under what condition it should operate. The specification document includes all key parameters such as input and output signals, operating frequency, memory requirements, interface, and communication protocols to be used. This document acts as a blueprint for the architecture and design teams, providing a precious guideline that ensures all the members work towards the same design goals. The output of this stage is functional and design specification, which becomes the foundation for next step, the architecture design phase. In short, specification translates the initial idea into a well-defined measurable set of design objectives that guides the rest of the design flow. In this stage, the specifications are converted into a block level design. Here, designers define how each component interacts with one another to achieve the desired functionalities. The architecture phase also decides important aspects like clock domains, power domains, and the main data flow across different blocks. The final output of this stage is an architecture diagram along with the module level description that acts as a foundation of RTL design. Once the architecture is finalized, the next step is RTL coding, that is register transfer level design. In this stage, the architecture is implemented using hardware description languages such as Verilog or VHDL. RTL coding describes the logical behavior of the digital circuit, meaning how data moves between registers and how the logic operations occur rather than its physical layout. It's very important that the code is synthesizable, meaning it can be converted into actual hardware during synthesis, and it should be modular so it can be reused in other designs. The final output of this stage is the RTL code, which represents the behavioral model of the chip ready for verification and synthesis. After the RTL coding is complete, the next important step is functional verification. This phase ensures that the RTL design behaves exactly as expected. In other words, it verifies the logical correctness of the design. We use test benches and simulations tools such as ModelSim, VCS, and Xilinx Vivado to check the design under different scenarios. During this stage, we test for both normal functionality and corner cases to identify and fix any logical or timing related bugs before the synthesis process begins. The final output of this stage is a verified RTL code along with the detailed simulation reports, ensuring the design is fully functional and ready for synthesis. After verification, the next most important step is RTL and logical synthesis. RTL synthesis and logical synthesis refers to the same process. RTL synthesis converts the RTL code written in Verilog or VHDL into a gate level netlist using standard cells from a technology library. During this process, the tool ensures that the design meets timing, area, and power constraints. In simple terms, it translates high level behavioral code into real hardware logic, the physical gates that will later be implemented on the chip. Now, moving to the logical synthesis, its broader concept that converts the entire logic optimization process. It includes a step like Boolean optimization, a technology mapping, and constraints driven optimization. The main aim is to ensure the design is functionally correct, efficient, and optimized for implementation. Overall, RTL synthesis is a subset of logical synthesis focusing on converting the RTL design into gate level hardware. The gate level netlist is a technology mapped representation of circuit generated after RTL synthesis. It enables STA, which is static timing analysis, by providing detailed path delays and cell level timing information. It can be functionally verified through gate level simulation, which is GLS, to ensure the synthesized design still behaves correctly. The netlist contains technology specific details like timing, power, and connectivity used by downstream EDA tools. The final output is a technology mapped Verilog or EDIF file representing the fully synthesized logic network. This stage focuses on validating the synthesized design to ensure that it functions correctly, meet timing constraint, and is ready for manufacturing. We starts with the gate level simulation, which verifies the synthesized netlist behaves same as the RTL. Next is static timing analysis, which ensures that all timing paths meet setup and hold time requirements for proper operation. We perform a logical equivalence check to confirm that there is no mismatch between the RTL and the synthesized netlist. Then, power analysis is carried out using gate level switching data to estimate dynamic and leakage power. DFT insertion or design for test adds scan and boundary scan features to make post silicon test easier. Finally, fault simulation and ATPG are used to validate test coverages, followed by sign off verification, confirming that the design is functionally correct, timing clean, and test ready. After the synthesis stage, we move to the physical design phase. Step converts the netlist, which is a logical representation of a circuit, into an actual chip layout. It involves several key stages like floor planning, where we define the chip's structure and allocate the space for different functional blocks. Then placement, which determines the exact location of all standard cells. Then routing, where interconnections between cells are created. And clock tree synthesis, which ensures that the clock signal reaches all the parts of the circuit with minimal delay. During this stage, we also optimize for power, timing, and signal integrity to ensure the chip performance reliability. Finally, the output of this stage is the physical layout database, commonly in the GDS format, which is then used for fabrication. So, once the physical design is complete, we move to the layout verification stage. Here, we ensure that the layout perfectly matches the intended schematic and follows all the fabrication rules. The key checks include DRC, which is Design Rule Check. It verifies that the all geometrical design constraints are met. Then LVS, also called Layout versus Schematic. This ensures that the layout connectivity exactly matches the schematic. And then ERC, which is Electrical Rule Check. It validates correct power and ground connections. Once these checks are clean, we get a verified layout that's ready for the tape out, meaning it can go for fabrication. After the layout verification is complete, the final GDSII file is sent to the semiconductor foundry. Here, the foundry uses a process called lithography to physically print the circuit pattern onto a silicon wafer. This is where our design turns into a real physical chip. The output is a silicon chip, which then goes through testing and packaging before being integrated into an electronic device. So, the conclusion of my today's video is that the entire VLSI design process is a systematic journey that transforms an idea or concept into a working silicon chip. Each stage from specification, design, verification, and synthesis to physical implementation and fabrication plays a crucial role in creating a reliable and high performance IC. At every step, proper verification and validation are essential to ensure functionality, power efficiency, and manufacturability. The process also demands a strong collaboration between design, verification, and testing teams. In essence, VLSI design bridges the gap between theoretical electronics and real world hardware. As we say, from concept to chip, VLSI represents the art of turning ideas into a silicon solutions. So, wrapping up today's video, I am truly happy to have you here and I can't wait to continue this amazing journey into VLSI design with you. Together, we will learn how to turn ideas into real silicon step by step in most fun and practical way possible. Before our next session, make sure to review your digital electronic basics for better understanding. Also, please install Xilinx Vivado or try EDA Playground. We will begin hands-on Verilog and RTL coding in upcoming sessions. If you are excited to learn VLSI in simple and practical way, don't forget to like, subscribe and hit the bell icon so you never miss a lesson. Let's begin this exciting VLSI journey together from concept to chip. Thank you.